Alright guys, welcome back. This is going to be week 4 of notes and homework, and I had told a few of you on our Google chat this past Friday that I thought I was going to move into our trig functions, which are sine, cosine, and tangent. I thought I was going to do that this week, but there was this one other topic in between what we just did, our special right triangles, and before the trig functions. So I'm still going to go ahead and do it because it does have some important vocab. They're not a huge part of our trig unit, but it is new vocabulary. So I'm going to go ahead and talk about our similar right triangles and then this next vocab term called our geometric mean. So we're going to do this for this week, and then you'll obviously have a homework assignment too. And then the following week, we are going to do our trig functions, which are those sine, cosine, and tangent terms that you've seen on map tests and on the practice air test. So that's the big thing in this unit. So we'll do that next. But before we do that, we're going to talk about a couple theorems, mainly involving geometric mean. And we're starting with our right triangle similarity theorem. Okay, so we have this term called an altitude. All right, we have mentioned it, I believe, once before. This line right here, I'm going to point with my arrow to the altitude, and the altitude is just a line that you can create in a right triangle that goes from an angle, okay, and makes a perpendicular line, okay, makes a right angle with the opposite side that it runs into. Okay, so it starts at a vertex, all right, where two sides meet. It creates a right angle with the side that's across from it. Okay, so that's why originally there was not this right angle there, and we just had one big right triangle right there. But now that you put an altitude in it, it creates a 90-degree angle within the triangle. So in the diagram to the right, actually before I write that similarity statement, let me just talk about what this theorem says. It says if the altitude is drawn to the hypotenuse, all right, remember a hypotenuse is across from the original right angle. So if it's drawn to the hypotenuse of a right triangle, then the two triangles formed, because we formed this triangle here and this triangle here, are similar to the original and to each other. Okay, so here's our original, it's the big one. These two triangles within it were created from this altitude. So our theorem says that as long as this altitude is drawn to the hypotenuse, which if we turn this to the side, okay, our original right triangle was here. Here's our right angle, so across from it is the hypotenuse. So as long as that altitude is drawn to the hypotenuse, then the three triangles now, the three right triangles are all similar to each other. So let's just write a similarity statement for those three. Now, similarity statements, remember, you have to keep the same order. So there's more than one way to write them sometimes, but I'm just going to go with one particular order and say that triangle ABC is similar to, now we've got these two created within triangle ABC. And since I named ABC the way that I did, all right, I named it by naming the longer leg and then the shorter leg, okay, A to B and then B to C. So for my next triangle name, I'm going to have to use the same order, all right? I'm going to name the bigger of the two triangles created within involving the letters A, B, and D. Now I have to write them in this order though, A, D, B, because in this right triangle that was created by the altitude, A to D is the longer leg, and then D to B is the shorter, sticking with the same order from the first. Now we've got one more to write. Okay, so sticking with the same order, we've got this triangle over here involving the letters B, D, and C. Now I have to write them in this order because, again, we're starting the name with the longer of the two legs. Okay, so going down to the right angle, B to D, and then D to C. So this is our similarity statement for the triangle shown to the right. Now, this next question that I have circled just tells us to basically do the same thing, but then sketch the three triangles so that the corresponding signs and angles have the same orientation. So with this original big right triangle that you have, there's an altitude drawn, and it is drawn to the hypotenuse. Okay, so our original triangle has this right angle, making this the hypotenuse. So we can use our similarity theorem. But what this question wants us to do is make a similarity statement, okay, identify the similar triangles, and then sketch them so that they're all facing the same way. All right, so I am going to start with our bigger triangle. And I'm going to call that triangle P, whoops, that is an R, don't want that yet, P, Q, R. Okay, so what I did with this name is I identified the legs basically first, P to Q and then Q to R. Okay, the longer leg and then the shorter leg. All right, so the other two triangles I have to name the same way. So I'm going to name the smaller of the two triangles created by the altitude. I'm going to name this one first using the letters Q, S, and R. Okay, but since the first name talks about the longer leg being first, PQ, and then the shorter leg being second, that means I have to name Q and S first because Q and S make up the longer leg of this smaller right triangle. So then R is going to be last. S to R is the shorter leg. All right, let's name our third triangle here, which involves the letters P, S, and Q. Okay, if I stick with the same order, then I have to call this triangle P, S, Q, because we have PS leading up to our right angle here. Okay, PS is the longer of the two legs, and then you have SQ, which is the shorter of the two legs. So that's our similarity statement. All right, we identified them. Now we have to sketch them so that they're all facing the same way. So I'm going to do triangle PQR first. All right, so it's just a sketch, doesn't have to be beautiful, but you gotta put your right angle in there. Now I'm gonna label this with the P up here at the top and the R being down here. Okay, so I kind of switched the way that this was facing. Right now, this original right triangle has the right angle over here and the hypotenuse over here. I basically turned it around so that the hypotenuse is over here on the right. Okay. All right, so I'm gonna name, let's see, I think the next biggest one technically is our P, S, and Q triangle. So I'm gonna have that facing the same way as the first one I just drew. So I'm gonna put my right angle there. Now, in order to label this correctly and match up our corresponding sides, I'm gonna have to have the P up here, the S here, and the Q. Okay, so I'm taking this triangle right here. So here's my right angle, and I am basically turning it over. I have to match up corresponding sides and draw it the same way. So you can always match up corresponding sides by looking at your similarity statement. And as long as you made a correct one, you can match up sides that way. So if I have PQ over here on the left, well, PQ are the first two letters. And then with the PS and Q triangle, okay, which is my third one that I listed up here, P and S are the first two letters. So I know that P and S have to be on the left side of the triangles that I drew. Now, I drew this one second because I wanted to show you that it was the second largest of the three. So I'm going to draw the smallest one last, okay, which is our Q, S, and R. So this little guy over here. Now, the first two letters are Q and S. So that means they have to go in the same spots as the first two letters did for the other triangles, which would put R down here. Okay, so we drew them with the corresponding sides and angles matching up, and they're facing the same way. Okay, so let's talk about proportional sides here, because similar means that the sides are proportional, the angles are congruent. So in this one example, I'm just going to do one so that you can see it again, but we did a whole unit on similar shapes, so this should be familiar. It says find the value of x, which is our altitude right here. So we had this original right triangle, and altitude was drawn to the hypotenuse, and they called it x. All right, so if I wanted to find x, okay, well, I've got to match up some corresponding sides. So with this triangle here, okay, remember, we've got two triangles created within, and then you have the original. Okay, well, this x right here, okay, I have technically one of the legs in that right triangle, and then I have the hypotenuse. Well, in order to write a proportion and solve for a missing side, you have to use the same two corresponding parts in another triangle. Okay, so if I use, let's say, the x and the 12, all right, what I'm using is a leg of this right triangle and the hypotenuse. Okay, well, the only other two numbers I have are a 9 and a 15. Luckily, the 15 is the hypotenuse of the original, and the 9 is the corresponding leg. Okay, it's the shorter of the two legs, just like x is. So that means 9 would go with 15. X is to 12 as 9 is to 15. So this is just a matter of our cross multiplying and solving for a missing part. Okay, x times 15, 9 times 12. And when you do that, you get 108 equals 15x. And then when you divide by 15, you get 7.2. All right, so that's just a quick review kind of our similar shape unit, where you cross multiply and then divide. Now here's where we get to our new terms, okay, geometric mean. I'm only going to do one example of the problems below the definition because we have something a little bit more complicated on the next page. Okay, so this term geometric mean, I'm going to draw a ratio first, so hopefully the definition makes a little bit more sense. Okay, so what the geometric mean is it's a mean of two positive numbers, we'll call them a and b. Is the positive number x such that a over x equals x over b? So if you're finding the geometric mean of two numbers, let's call them a and b, this is how you would set up your ratio to find that geometric mean. So if we cross multiply, just like we do in our ratios, okay, what we would get is x times x, which is x squared. A times b is just ab, okay? Technically there'd be multiplication in between, but if you write them right next to each other, that means multiplication. So x squared would equal ab, and you could also express it this way. If we were solving this right here for x, what we would do to get rid of that squared is we would square root both sides. So technically, x also equals the square root of ab. Okay, so this is how you would find the geometric mean of two positive numbers. So an example that we have here is 6 and 30. Find the geometric mean of that pair of numbers. All right, well, technically, x is the square root of those two numbers multiplied together. So if I write x equals the square root, it would be 6 times the 30. So that would give you the square root of 180, which means the geometric mean of those two numbers is 13.4. Okay, and we'll just do one of those examples because I think you can see what you're doing with two positive numbers pretty easily. So I am going to move this paper to the second part of these notes, okay, which I've also taken some problems out and just tried to keep it basic. All right, so I'm going to move this. Now we're still talking about geometric mean, which is new, but we're involving our other parts of a right triangle here. Okay, we have two more theorems. And the first theorem is the geometric mean altitude theorem. This theorem says that the length of the altitude is the geometric mean of the lengths of the two segments. Okay, so we've got this picture of a right triangle over here. The original is ABC, and it has this altitude drawn right there. Okay, so BD is the altitude. So since it says the altitude is the geometric mean, okay, I'm going to take what we had just written down for geometric mean. So x squared equals the other two positive numbers multiplied together. Or you could write the square root of multiplying those numbers. So technically, BD squared should equal the length of the two segments that it runs into. All right, here's our altitude. The segment that it runs into is down here, but it says the length of the two segments. So you've got one here and the second one there. So A to D is one of those two segments, and then D to C is the other part. So the way we would write this is AD, so the length of AD times the length of DC. Okay, so let's see how that plays out in an example with some new numbers. So it says find the value of x. All right, well in this first picture here, x is the altitude. So technically, since that altitude squared should equal the two segments that it runs into multiplied together, this is what the setup would look like. X squared, here's our altitude. All right, this was our original triangle. The altitude runs into the hypotenuse. Okay, so x squared should equal this segment times this segment. 8 times 12. So x squared equals 96. Now, if you're solving for x, you would do the opposite to both sides, which is to take the square root. So the square root, and that cancels that out, the square root of 96, I've already written these down so that I didn't have to have my calculator under the light here, but the square root of 96 is 9.8. So the length of the altitude is 9.8. Okay, next one. Same deal, just a little bit of a different triangle. So we have a right triangle with an altitude right here where the x is, and it does run into the hypotenuse of the original right triangle. Okay, so again, it's the altitude squared equals the two segments that it runs into multiplied together. Now this 37 though extends from one end of the leg to the other, or the original hypotenuse. So we're not going to do 37 times 5, we're going to do 32 times 5. Okay, so x squared equals 160. If you take the square root of 160 to do the opposite, then the square root is 12.6. All right, last example, and then we'll do 2 more examples with our next theorem. Okay, so in this one, we are actually given the length of the altitude. So here's our altitude. Our original right triangle is right here, and the altitude runs into our hypotenuse. Okay, so we have our similar triangles. Except instead of writing x squared, I'm going to write 18 squared, since that's the altitude. So the two segments that it runs into, that the altitude creates, are x and 15. So we still want to multiply those together. Okay, well 18 squared, you can actually solve that out to 324. 15 times x is just 15x. So if we're solving for x, we want to divide both sides by 15. And x is going to equal 21.6. Okay, so we still solved for x, we just used the theorem a little differently. Okay, now this last one, all right, is going to have 2 examples that goes with it. It's another geometric mean theorem, but this one's called the leg theorem. So the one that we just had was the altitude theorem. This one is the leg theorem. The wording is a little confusing, so I'm going to write out, obviously, what it means based on the picture to the right, but here we go. It says the length of a leg of the triangle is the geometric mean. So in the last one, the altitude was the geometric mean. Now the leg is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to that leg. Okay, so adjacent means next to, so keep that in mind. Next to. Okay, so based off this picture here, all right, this right triangle has legs AB and legs BC. Okay, because this is the geometric mean leg theorem. So this is a leg and this is a leg. Okay, so the leg is the geometric mean, which means if I'm talking about leg AB, I'm going to write AB squared. Okay, it's not the altitude squared this time. Now it says that it's the leg and the length of the hypotenuse and the segment of that hypotenuse next to the leg you're talking about. So AB squared equals, all right, well here's the hypotenuse of the original right triangle. Okay, so the hypotenuse is AC. But it says the hypotenuse and the segment of that hypotenuse next to that leg. Well, here's the leg we're talking about. So the segment of the hypotenuse that's next to it is right here. So we're going to multiply it by that segment AD. That changes, however, when we're talking about the other leg, BC. So I'm going to start this one with BC squared. All right, BC is the other leg of the original right triangle. So BC equals, now same thing though, the hypotenuse is AC. So AC has got to be in there. However, the segment of that hypotenuse AC that's next to this leg is this one. So I'm not talking about segment AD, now I'm talking about segment DC. Okay, so this is a lot to remember, a lot of technical terms, but it's all basically set up the same way around this geometric mean. Okay, so this is asking us to find the value of x. Well, in our original right triangle, okay, this is a leg, and this is a leg. So we are asked to find the length of this leg here. So what we're going to do is use this formula. I'm going to write x squared, because this is the leg theorem, so I'm going to square that. Equals, here's our hypotenuse. I'm going to call it h. Okay, it's across from the original right angle. So our hypotenuse is 26. If we add together this 24 and this 2, we get 26. Now, since we're trying to find this leg, our formula has to have the hypotenuse and the segment of the hypotenuse that's next to the leg you're talking about. In this case, it would be the 24. So you would end up with x squared equals 26 times 24, which is 624. And then you square root both sides to solve for x, which you get. And this ended up being a decimal that rounded up to 25. So this is an approximate. Maybe I should write this squiggly equal sign because it's approximate. Okay? All right. Last example for the notes, and then we're going to stop this video. So we're asked to find x, which here's our original right triangle. So this is a leg, and this is a leg. All right, here is our hypotenuse. So where this 12 is referring to, that's your hypotenuse. So we're going to solve for our leg. I'm going to call that x squared because that's the geometric mean. And then we have the hypotenuse as 12. Okay, so it's the hypotenuse times the segment of the hypotenuse next to the leg in question. Now this is the segment we're talking about right here. It's not labeled, but if we take 7 away from 12, that part ends up being 5. Okay, so you have x squared equals 60. Take the square root of both sides. The square root of 60 is 7.7. Okay, so these are our two theorems. One of them uses the leg for the geometric mean, and the other uses the altitude. Okay, so we have finished our notes. We finished our examples. I am going to post this video link, and then I will post a picture of your assignment. So make sure to reach out to me during the week if you have questions. You can join our Google Hangout on Friday, and make sure that you're submitting or sending me pictures of both your notes and your homework, because if I don't get both by the end of the week, I'm going to have to mark them as missing. So please reach out if you have questions.